Today on Applied Science, I'd like to talk about how digital light projectors work. And so to demonstrate this, I made a macro scale digital mirror chip, which we'll have some fun with. And then also we'll zoom way in and check out what an actual DLP chip looks like under the scanning electron microscope. Okay, so let's get started. Almost all projectors work on the same basic principle. You start with a light source, you filter the light source based on the image data that you want to display, and then you use a lens to transfer that image from within the projector out to a projection screen. So in a film projector, it's pretty straightforward. We've got our light source, you pass the film in front of it, and then you use a lens to transfer that image to the screen. And in an LCD digital projector, we'd have basically the same thing, but the plane of the film is replaced with a liquid crystal, which allows the light through in certain areas and not in other areas. So we have pixels that are clear and pixels that are opaque. One problem with liquid crystal display projectors is that you sometimes need 3 separate LCDs for the colors, red, green, and blue. And this complicates the optical path quite a bit because you have to combine those 3 colored optical paths back into one. This DLP projector gets around the problem of requiring 3 separate light paths like a lot of LCD projectors do, and so it's cheaper and has better performance characteristics in some areas. So let me show you what's inside this thing. We have a bulb, and this is a high-intensity discharge bulb like a mercury vapor lamp, and then a lens to get the light in a nice column from this light bulb, because normally it's just spraying out in all directions, but we want to have a column of light on this special DMD device, and DMD stands for Digital Micro Mirror Device. I should note that DLP stands for Digital Light Processing, which is a trademarked name, kind of like Xerox. It's become a very common way to describe this, but that's actually a trademark name owned by Texas Instruments. And the digital mirror device is an array of tiny mirrors, and when the mirror is facing in the right direction, it shines light through our main projection lens, and then it forms an image out on the projection screen here. So it's basically the same thing as an LCD, but instead of the pixels being clear or opaque, the pixels are either a mirror that's turned in the right direction to shine light through this, or they're turned away so that the light doesn't shine through the lens. I owe a big thanks to Mike's Electric Stuff for donating this DLP chip to my channel here, and I cracked it open. This is actually what the case looks like. And I opened it up, which took quite a bit of doing. Originally I thought that the case was soldered shut, but it's actually been welded, and so I ended up using a Dremel just to grind away the casing here and opened it up. And this is what the chip actually looks like. So as you can see, it just looks like a continuous mirror, but actually there's many thousands of tiny little mirrors that represent 1 pixel each on the surface here. So to get a better understanding of how this works, I made a macro scale model. So let's take a look at that. This is a model of the digital micro mirror device that's in the projector. And as you can see, it's built with a whole bunch of individual mirrors. And just like in the real DMD chip, each mirror has its own little hinge. And so I built this by starting with a plastic grid and hot gluing down some thread across the grid openings. And then I cut out a whole bunch of small mirrors from a piece of mirrored acrylic and glued those down with a washer on the back. And the original plan was to make tiny little magnets, electromagnets, winding them on my lathe, and then putting an electromagnet behind each mirror, and so then I could move the mirror with an electromagnet. And I did actually get this working. It drew about 300 milliamps, I think, at 3 volts or so to get the mirror to move. However, I scaled up the effort mentally required to do this for, 16 or 25 or 36 mirrors. And it wasn't going to happen today. So I came out with another way of showing this that's a whole lot easier. Here's all the washers on the back of each mirror. I can affect them all globally just by using a really big magnet. So it's true I don't have image control. Originally I was going to have a microcontroller actually control the electromagnet so I could generate a primitive image with this thing, which I might still do at some point if I have enough time. But I think this is more than good enough to show the concept. Just keep in mind that the real digital mirror device uses electrostatic attraction, which we'll talk about later, and I'm actually using a magnet. This would just be permanent magnet attraction just to show the thing in motion. Here's the model in action. As you can see, I've got a light source set up and it's shining on the mirror array, and then as I pass the magnet back and forth behind the array, you can see the pixels turning on and off on the projection screen. And the trick is when the mirror is reflecting the light through the projection lens, the image is transferred from that array of mirrors out to the projection screen. And if the mirror is tipped away, the light just goes scattering off in some direction that doesn't go through the lens. So internally, inside the projector, there has to be a light dump, basically. So the mirror is either facing the light, directing the light out through the projection lens, or it's directing the light into basically a black panel that just absorbs all that extra light. So you might be wondering how this actually reduces the complexity from a liquid crystal display projector. Like, why would we invent DLP if we already had LCD working? And also, I didn't see anything about colored light paths in DLP. If we've got the mirrors working here like this, how do we actually get different color pixels? And the answer is in that most DLP projector systems, there's a color wheel that's spinning in front of the light source. So some of the time the light is green, and then there'll also be color filters for red and blue and sometimes even additional colors. So the trick is that we break the image up such that when the green filter is in place, we adjust the mirrors so that we get the green channel of our image, and then when the color filter rolls around to red, we change the mirrors around to display the red channel. And if we do this quickly enough, your eye blends them all together. However, you can see the separation of colors. If you're looking at an image from a DLP projector and you move your eyes quickly by it, you can actually see the image separate into red, green, blue. The mirrors have to move exceptionally fast to make this scheme work. In fact, even more interestingly, the mirror is either on or off. Like, we can't make a pixel gray like we can with a liquid crystal display. In an LCD, we can just give the pixel half voltage and it will be semi-transparent, so we get a gray value. But the mirror is either directing light through or it isn't. So the way that we get gray values with a DLP projector is just to switch the mirror on and off exceptionally fast. The mirrors are so small that they can move from off to on in just 5 or 10 microseconds even. So the chip is able to switch the mirrors quickly enough to make a gray level appear. Let's take a close look at the DLP chip. This is an image of the chip in my standard light microscope at the highest magnification setting. And each mirror, you can make out the grid of mirrors. Each mirror is about 10 microns on an edge, on the order of a red blood cell. In order to get a clearer view of the actual mirrors themselves, we need to use a scanning electron microscope. So I loaded the chip into my SEM and got some very close-up photos of the mirrors. This region of the chip was damaged. I basically took a pair of tweezers and just ever so lightly touched the surface of the chip. And just the very slight amount of pressure that the tweezers put on there just completely blew off a few mirrors. This is good because now we can see the suspension mechanism that actually holds the mirror in place and allows it to pivot back and forth. And you can see that the pivot, the hinge, is actually a torsional hinge, just like it is in my macroscale model. So instead of a piece of thread, it's a piece of silicon that does the hinging, and the mirror tips diagonally from corner to corner. Remember that the force that causes the mirror to move is electrostatic, and so the chip operates at something around 10 volts or something like that, and just the attraction from the mirror, which is held at one potential, relative to the potential of the electrodes at each corner of the mirror is only probably about 10 volts or 20 at the most. This allows for very fast operation because as soon as the voltage disappears, there's no more electrostatic attraction and the mirror will snap back to its resting position. Another drawback of LCD projectors is that you lose half the light right off the bat because of the polarization filters needed to make a liquid crystal display work. We don't have that problem with DLP projectors because there's no polarization necessary. This means that you can get away with a much smaller light source for a DLP projector, and then that reduces the whole cost of the projector because you don't need as big of a power supply or as big of a light bulb and so on. Even with the added difficulty of the color wheel and the really high bandwidth needed to drive the DLP chips, it's still quite a competitive display technology compared to LCD. Okay, hope you found that interesting. See you next time. Bye.